The paper by Tatsuo Iguchi and Masahiro Takayama delves into the motion of a homogeneous and inextensible string of finite length L under the influence of gravity and tension. One end of the string is fixed, while the other is free. The string's position at time t is described as a curve x, s, t, equals, x1, s, t, x2, s, t, x3, s, t, where s is the arc length measured from the free end. The fixed end is assumed to be at the origin in R3, with a constant density of the string. G is the acceleration of gravity vector, and tau, s, t, is the scalar tension of the string at the point x, s, t, at time t. The paper focuses on the initial boundary value problem for the equations of motion of the hanging string, both with and without external forces. In this problem, the tension of the string is an unknown quantity, determined by a unique solution to a two-point boundary value problem derived from the inextensibility of the string and the equation of motion. This tension degenerates linearly at the free end, necessitating the use of weighted Sobolev spaces for a priori estimates. Under a natural stability condition, the authors derive a priori estimates for solutions to the initial boundary value problem in these weighted Sobolev spaces. They also prove the uniqueness of solutions to the problem. The necessity for the weights in the Sobolev spaces results from the degeneracy of the tension, which is a key aspect of the analysis. The research contributes to the understanding of the dynamics of inextensible strings under gravity and tension, providing new insights into the mathematical modeling and analysis of such systems. The paper's findings have implications for various fields, including physics, engineering, and applied mathematics, where the motion of strings and other unidimensional objects is crucial. The motion of the string is described by the equations of motion and inextensibility, where ρ is the density of the string, x is the position of the string, tau is the tension, g is the gravity vector, and L is the length of the string. The equations are derived from the physical laws governing the string's motion, and the inextensibility constraint is imposed to ensure the string's length remains constant. The boundary conditions are specified, where one end of the string is fixed at the origin, and the other end is free. By making a change of variables, the problem can be simplified to consider the case where ρ equals 1, L equals 1, and g equals 1. The resulting initial boundary value problem is formulated, consisting of the equations of motion and inextensibility, along with the boundary and initial conditions. This problem also arises from a minimization problem of an action function, where the tension tau appears as a Lagrangian multiplier. The tension tau is an unknown quantity, and by using the inextensibility constraint, an equation for the tension can be derived, which is a two-point boundary value problem. The paper delves into the time-dependent nature of the string's tension, a fundamental aspect of the problem. By differentiating the constraint, x2 equals 1 with respect to time, the authors derive equations that relate the string's curvature and deformation velocity to its tension. This non-local dependence on the curvature and deformation velocity is a key feature of the problem. The authors then introduce a stability condition on the tension, which is necessary for the well-posedness of the initial boundary value problem. This condition is relaxed compared to standard theories, as positivity of the tension fails at the free ends. The paper aims to establish the local well-posedness of the problem in weighted Sobolev spaces under this stability condition. The authors will derive a priori estimates for the solution, which is a crucial step towards achieving this goal. The authors discuss the uniqueness of solutions to the problem in the class where a priori estimates would be obtained, as given in theorems 2.3 and 2.4. They consider the initial boundary value problem to hyperbolic equations, coupled with the two-point boundary value problem, as an alternative approach to solve the original problem. This transformed system consists of equations 1.7, 1.4, and 1.3. The authors note that a boundary condition on the free ends is not necessary due to the degenerate tension at s equals 0, as explained in Takayama, 16. They aim to show that the solution to the transformed system satisfies the constraint, x equals 1 under appropriate conditions on the initial data. To achieve this, they will use an energy estimate and prove in theorem 2.5 that if the initial data satisfies certain constraints, any regular solution to the transformed system satisfies the constraint, x equals 1. The authors also review previous studies on the well-posed-ness of the initial boundary value problem, including Riken's work, 11, 12, on the motion of an inextensible string of infinite length and Preston's work, 7, on the motion of an inextensible string of finite length. These studies used different approaches, such as the hard implicit function theorem and discretization methods, to construct solutions. However, the authors' approach is distinct from these previous studies. The authors consider the initial boundary value problem, 1.1, 1.3, for an inextensible string, which has been studied previously by Diarasis ul and Vorotnikov, who proved the existence of a generalized Young measure solution. However, the well-posed-ness of the problem remains unresolved. The authors aim to establish well-posed-ness in weighted Sobolev spaces, following Riken and Preston. The problem is related to the motion of an inextensible string, which has been studied in various contexts, including geodesics on an infinitedimensional manifold of inextensible curves, gradient flows, and rotations of an inextensible hanging string under gravity. The study of the motion of an inextensible string has applications in textile industry and flapping dynamics of a flag. The weights in the norm used in this paper arise naturally from the standard theory of hyperbolic systems. By linearizing the problem around a trivial stationary solution and introducing a new quantity x-sharp, the authors transform the linearized problem into a well-posed initial boundary value problem in a weighted Sobolev space Xm. This space is the same as that used by Riken and Preston. The authors will evaluate the solution X of the problem in the weighted Sobolev space Xm using the energy method, which requires evaluating the solution tau of the two-point boundary value problem, 1.4, in a weighted Sobolev space. The solution tau will be expressed using Green's function of the problem, and precise pointwise estimates of Green's function will be used to evaluate it. The research paper is structured into 10 sections, with the main results presented in Section 2. These results include a priori estimates for solutions in Theorem 2.1, uniqueness of solutions in Theorems 2.3 and 2.4, and the equivalence of the original problem and the transformed problem in Theorem 2.5. Section 3 analyzes Green's function related to the two-point boundary value problem to derive precise pointwise estimates for the solution in terms of norms of the weighted Sobolev space Xm for the coefficients. Section 4 presents basic properties of the space Xm and related calculus inequalities, and introduces another weighted Sobolev space Ym for convenience in estimating higher-order derivatives of the solution. Section 5 proves Theorem 2.5. While Section 6 analyzes a linearized system to the problem and derives an energy estimate for the solution. Section 7 proves Theorems 2.3 and 2.4 by applying the energy estimate obtained in Section 6 with a slight modification. Section 8 derives estimates for the tension tau assuming some bounds of norms for X and the stability condition. In the critical case of the regularity index, a weaker norm is used for tau. Section 9 evaluates initial values for time derivatives of X and tau in terms of the initial data. Finally, Section 10 proves Theorem 2.1. The notation used in the paper includes LP denoting the Lebesgue space on the open interval, 0, 1, hem denoting the L2 Sobolev space of order M on 0, 1, and XM denoting a weighted Sobolev space defined by a norm that involves the L2 norm and higher-order derivatives. The paper also introduces norms, M and M, asterisk operator for functions U equals U, S, T, depending on time t, which are used to evaluate X and tau respectively. In the critical case of the regularity index M, a weaker norm is used for tau. The paper acknowledges partial support from JSPSKAKENHI grant number JP22H01133. Theorem 2.1 offers a priori estimates for the solution, X, tau, to the initial boundary value problem under specific conditions on the initial data. It ensures that any regular solution will meet the stability condition, have a bounded norm, and exhibit certain properties of the tension function tau, S, T. This theorem is crucial for understanding solution behavior and identifying potential issues, such as ill-posedness, which can arise when the initial tension is negative everywhere except at the free end S equals 0. The requirement of M is greater than or equal to 4 corresponds to quasi-linear regularity, with m equals 4 being a critical regularity index in the classical sense. The uniqueness of the solution, x, tau, to the initial boundary value problem 1.1, 1.3, is analyzed. The solution class is specified as x, element of L infinity, 0, t, x2, intersection w1, infinity, 0, t, x1, which implies x, element of w2, infinity, 0, t, L2, by lemma 5.3. Assuming x, element of C0, 0, t, x1, intersection C1, 0, t, L2, the initial conditions, 1.3, can be understood in the classical sense. Theorem 2.3 ensures the uniqueness of the solution in the class, 2.3, satisfying the stability condition, 1.5. For the case g equals 0, if the initial deformation velocity σ1 is identically 0, the initial boundary value problem has a trivial solution that does not satisfy the stability condition. However, by lemma 7.2, this trivial solution is the only one that does not satisfy the stability condition. Theorem 2.4 guarantees the uniqueness of solutions in this case. Theorem 2.5 establishes the equivalence of the original problem, 1.1, 1.3, and the transformed problem, 1.7, 1.4, and 1.3, under the assumptions that the solution satisfies the stability condition, 1.5, and the initial data satisfies certain conditions. The two-point boundary value problem, 3.1, is then considered, where xs and hs are given functions and a is a constant. The Green's function to this boundary value problem is constructed using unique solutions to the initial value problems, 3.2 and 3.3. I'm sorry, but I don't have the capability to directly access or modify external content. However, I can provide guidance on how to refine the transcript based on the guidelines you've provided. Would you like me to outline the steps or offer suggestions on specific aspects of the transcript? Lemmas 3.2 and 3.3 provide crucial insights into the properties of functions psi and phi, which are solutions to specific differential equations. Lemma 3.2 establishes that psi, s, is non-increasing and bounded between 1 and express sigma 1/2 x, L2, with psi, s, being non-decreasing and bounded below by sigma 1/2 x, L2 express sigma 1/2 x, L2. This lemma also proves that psi, s, is strictly positive for all s element of 0, 1. The proof involves showing that psi, s, cannot have a 0 in the interval 0, 1, and then using the differential equation to bound psi, s, and psi, s. These bounds on psi, s, and psi, s, are essential in understanding the behavior of function psi, which is critical in the subsequent analysis. The positivity of psi, s, ensures that the function remains well-defined and bounded throughout the interval 0, 1, allowing for meaningful interpretations of the results. The authors establish estimates for solutions to the boundary value problem by proving a series of lemmas. The first lemma provides an estimate for the derivative of a solution, phi, in terms of the initial data and the function h. This involves integrating the equation for phi over 0, s, and using the initial condition phi, 0, t, equals 0, followed by applying Gronwall's inequality to obtain an upper bound for phi, r. The second lemma deals with the case where hs is non-negative, deriving upper and lower bounds for the solution tau, s, using Green's function. These estimates are crucial for understanding the behavior of solutions under certain conditions on hs. The positivity of tau, s, ensures an upper bound for tau, s, and subsequently for tau, s. The lower bound for tau, s, is derived by integrating the absolute value of x, sigma, squared, multiplied by tau, sigma, with respect to sigma from 0 to s. This yields the desired estimate. The paper then presents lemma 3.5, which provides estimates for the solution tau to the problem, 3.1, without assuming non-negativity of hs and a. Specifically, for any m greater than 0, there exists a constant c equals c, m, greater than 0 such that if the L2 norm of x is bounded by m, then the solution tau satisfies the estimates tau s is less than or equal to c a s plus saw L1's 1 minus alpha, and s alpha tau s is less than or equal to c a s alpha plus saw L1 for any s element of 0, 1, and any alpha element of 0, 1. The proof of lemma 3.5 relies on lemmas 3.1 and 3.2, which imply that phi s asymptotically equal s, phi s asymptotically equal 1, psi s asymptotically equal 1, and s psi s 1. Using the expression for tau s in equation 3.5, the estimates for tau s and s alpha tau s are derived. To address the singularity in Hs at s equals 0, the paper introduces lemma 3.6, which provides a calculus inequality for evaluating the singularity in terms of LP-norm. Specifically, for 1 is less than or equal to p is less than or equal to infinity and alpha plus 1, p greater than 0. The inequality states that S alpha HLP is less than or equal to 1, alpha plus 1, p, 1, ps alpha plus 1 phl1, where h is equals integral shish, sigma, d sigma. The authors continue to develop their theory by providing a proof for a specific case, assuming p is finite and hs is non-negative. They leverage integration by parts to derive an estimate, which is then used to prove a lemma. This lemma states that for a given m, there exists a constant c such that if the solution tau satisfies a certain L2 norm, it also satisfies an LP norm with a bound dependent on m and the function pH. The proof relies on previous lemmas and equations, showcasing the interconnectedness of the author's arguments. This section delves deeper into the mathematical derivations, emphasizing the technical aspects of their theory. This section of the research paper delves into the weighted Sobolev space XM, a concept introduced by Rikin, 11. The space XM is defined as a collection of functions U, characterized by a specific norm that is essentially equivalent to the norm in the L2 Sobolev space of order M on the unit disk D in R2. The norm, barred blue, barred blam is shown to be equivalent to the norm, barred blue sharp, barred BLHM, D, where U sharp, X, Y, equals U, X2 plus Y2, is a function on D. The paper presents several lemmas that provide essential estimates for various quantities. For instance, lemma 4.2 demonstrates that barred BL, SU, barred blam is bounded by barred blue, barred blam plus 2, while lemma 4.3 gives estimates for the LQ norm and L infinity norm of U in terms of its XM norm. These estimates are crucial for the subsequent analysis in the paper. Moreover, the paper highlights some important properties of the space XM. Unlike standard Sobolev spaces, U element of XM plus 1 does not necessarily imply U element of XM. A counterexample is provided, illustrating that the first derivative of a function in XM plus the first of may not be in XM. Furthermore, the embedding x2 right pointing arrow L infinity, 0, 1 is mentioned, which is vital for later results. Finally, the paper concludes with lemma 4.5, which provides a weighted L infinity estimate for derivatives of functions defined in 0, 1 in terms of XM norms. This lemma is significant as it establishes a connection between the XM norm and the L infinity norm of derivatives, further emphasizing the importance of the XM space in the context of the research. Lemmas 4.6, 4.7, 4.8, and 4.9 form a crucial foundation in understanding the properties of functions in various spaces. These lemmas establish estimates for the norm of a function, its derivatives, and the norm of the function itself, providing insights into the behavior of functions and their relationships with their derivatives. In lemma 4.6, integral inequalities are used to demonstrate estimates for the norm of a function in terms of its derivatives and the norm of the function itself. This is essential for comprehending how the smoothness of a function affects its norm. Building upon this, lemma 4.7 provides estimates for the norm of a function and its derivatives. These estimates are integral to the proof of lemma 4.6, emphasizing the interdependence between a function's norm and its derivatives. Moving on to lemma 4.8, it discusses the properties of functions in a compact set and their derivatives. It establishes relationships between the norms of the function and its derivatives, shedding light on the impact of compactness on function behavior. Lastly, Lemma 4.9 highlights the importance of a function's smoothness by providing estimates for the norm of a function and its derivatives. This underscores the significance of smoothness in determining the norm of a function and its derivatives. These lemmas collectively contribute to a deeper understanding of functions in various spaces, emphasizing the intricate connections between a function, its derivatives, and their norms. The proof on page 16 begins by addressing the case where j equals 0, which is trivial. It then proceeds to the case j equals 1, leveraging lemmas 4.6 and 4.5 to establish an estimate. For j greater than or equal to 2, the proof employs a different approach, involving the evaluation of a derivative and a summation. This section also introduces the concept of weighted Sobolev spaces, specifically Ym, which is defined for non-negative integers m. The space Ym is equipped with a norm that includes L2 forms of derivatives up to the kth order. The importance of this space is highlighted through identities like 4.1 and 4.2, which connect xm plus 1 and ym plus 1 spaces. This section's technical details and novel ideas are crucial for understanding the paper's methodology and contributions. Lemma 4.10 provides a critical estimate for the norms of U in terms of xm and xm plus 2, where m is a non-negative integer. This estimate relies on lemmas 4.3, 4.5, 4.6, and 4.7. For m equal to 0, 1, or 2, the norm of U in Y0 is bounded by the sum of norms of U in L4 and V in L4, as well as the norms of U and V in L infinity and L2, respectively. Similarly, the norm of U in Y1 is bounded by the sum of norms of U in L infinity and V in L2, as well as the norms of U and V in L2 and L infinity, respectively. When m equals 2k plus 1 with k is greater than or equal to 1, the norm of U in Y2k plus 1 is bounded by the sum of norms of U and V in X2k and L2, respectively, as well as the norms of U and V in L infinity and L2, respectively. This is established by applying equation 4.2 and lemmas 4.7 and 4.6. For m equal to 2k with k is greater than or equal to 2, the norm of U in Y2k is bounded by the sum of norms of U and V in X2k1 and L2, respectively, as well as the norms of U and V in L infinity and L2, respectively. This is also established by applying equation 4.2 and lemmas 4.7 and 4.6. These estimates are crucial to the proof of the main theorem, providing a deep understanding of the relationship between the norms of U and xm. They demonstrate the intricate interplay between the different Sobolev spaces and their norms, which is essential for establishing the regularity of the solution to the problem under consideration. The authors present lemma 4.11, which provides estimates for the norms of tau U, V, in various spaces under the assumption tau, S equals 0 equals 0. The lemma consists of 4 estimates, each corresponding to a different case of the parameter m. For m equals 0, the authors derive estimates for tau, S, bounding the norms of tau U, V, by the minimum of 2 terms involving the norms of tau, U, and V, in different spaces. The case m equals 1 uses similar techniques to bound barred BL tau U, V, barred BL Y1 by the product of the norms of tau, and U, or V. For m equals 2k, where k is an integer greater than or equal to 1, barred BL tau U, V, barred BL Y2k is expressed as a sum of 2 terms, each involving a summation over indices j0, j1, and j2. The first term is bounded by a sum of terms involving the norms of derivatives of tau, U, and V in different spaces. Throughout the proof, various inequalities and estimates are used to derive the desired bounds for the norms of tau U, V. The evaluation of integrals I1 and I2 is a critical component in the proof of a lemma related to the regularity of solutions for a certain partial differential equation. The analysis is divided into several cases based on the values of indices j0, j1, and j2, as well as the parameter m. For I1, 4 cases are considered, each involving the norms of U and V in function spaces such as x2, k1, x2, k plus 1, and x2, k plus 2. Similarly, the evaluation of I2 is split into 4 cases, with bounds also given in terms of the norms of u and v in function spaces. The estimates for I1 and I2 are then combined to obtain the desired bound for the lemma in the case m equals 2k. The case m equals 2k plus 1 is mentioned to be proven similarly, but the details are omitted for brevity. This section provides a detailed analysis of the integrals I1 and I2, utilizing various function spaces and applying lemmas to establish the required estimates. The averaging operator m is defined for a function u in the open interval 0, 1, calculating the average of u over the interval 0, s, for each s in 0, 1. The derivative of this average is then evaluated, revealing its relationship with the original function's derivative. A lemma and its corollary are also discussed, focusing on the estimation of functions in weighted LP spaces. These mathematical derivations and their applications are crucial for understanding the paper's methodology and contributions. The section of the paper demonstrates the equivalence of the original system and the transformed system under the stability condition. It starts with auxiliary estimates for solutions, assuming a class of functions. Specifically, it shows that the derivatives of the solution are bounded. The section then presents several lemmas that provide estimates for the solution and its derivatives, relying on previous results such as lemmas 4.6 and 3.4 to establish bounds. These estimates are crucial for the proof of Theorem 2.5, ensuring the equivalence of the systems. The technical details and mathematical derivations in this section are essential for understanding the equivalence of the systems. This section of the research paper is dedicated to proving Theorem 2.5, a pivotal part of the overall argument. The proof commences by assuming that x, tau, is a solution to the transformed system, adhering to the stability condition, and belonging to the class defined in equation 2.3. A new function, p, s, t, equals x, s, t, squared 1, is introduced, and h, s, t, is defined as p, s, t, 1 is defined. The objective is to demonstrate that h, s, t, is defined as 0, achieved through the analysis of the hyperbolic equation satisfied by h, along with its boundary and initial conditions. The time derivative of the energy functional E, t, is computed, which is defined as the integral of lambda s, h squared plus tau, h squared plus tau squared, h squared over the domain, plus a boundary term involving tt, h squared. Using integration by parts, the boundary conditions, and the hyperbolic equation for h, an estimate for the time derivative of E, t, is obtained. A key observation is made that, by selecting lambda sufficiently large, the energy functional E, t, is equivalent to the sum of the L-squared norms of sh, and sh. This allows the authors to conclude that the time derivative of E, t, is bounded by E, t, itself, implying that h, s, t, is defined as 0, as desired. Throughout the proof, the authors heavily rely on previously established results, such as lemmas 5.2, 5.3, and 5.4, which provide estimates for tau and its derivatives. They also utilize the standard Sobolev embedding theorem to control the L norm of h in terms of the L-squared norms of x and x. The proof presented in this section forms the basis for the subsequent arguments, and its technical details are crucial for establishing the main results of the paper. The evaluation of an integral related to the function h, s, t, and its derivatives is crucial for estimating the energy functional E, t, in a system with a linearized differential operator a tau. This process begins by bounding the integral of tt, leveraging the properties of h, s, t, and its derivatives to obtain a Gronwall's inequality that yields the desired result. In the context of a variable coefficient differential operator a tau, defined by equation 6.1, the original system can be rewritten as a second-order linear differential equation. A pivotal component of this section is lemma 6.1, which establishes an equivalence between the norms of x and a tau x under specific conditions on the function tau, s. This equivalence plays a vital role in further analyzing the system's behavior. To prove the lemma, it suffices to demonstrate the first estimate in the equivalence. Using the definition of a tau, the authors derive an expression for x, s, involving the averaging operator m. This expression leads to a bound on x, s, which in turn implies the desired estimate through corollary 4.13 with specific values for beta, j, and p. This result forms the basis for subsequent investigations into the properties of the system governed by the linearized differential operator a tau. The linearized system for the given problem is discussed, including equations 1.1, 1.2, and 1.4. The linearized system is presented in equations 6.2 and 6.3, where variations of x, tau, are denoted by y, nu. An energy estimate for solutions to this linearized system is derived in proposition 6.2, assuming certain conditions are met, such as 5.1, 6.4, and the stability condition 1.5. The energy estimate, E.t., is bounded by a function of initial energy, stability terms, and an integral of time-dependent stability terms. This estimate is crucial for understanding the behavior of the linearized system and its implications on the original problem. The system is overdetermined due to the second equation in 6.2, but a similar energy estimate can be obtained without using this equation by imposing additional regularities on x. The analysis focuses on the term n x, y, s equals 1 in the energy estimates for a solution to the hyperbolic system of equations. To evaluate this term, the authors utilize the fundamental solution in boundary conditions, rewriting it as a function of various quantities and their derivatives, leading to equation 6.9. This equation is crucial for further analysis and stability conditions. The authors also derive an auxiliary equation for nu, the time derivative of nu, by differentiating the original equation for nu with respect to time. The auxiliary equation, given in 6.11, helps in evaluating the remaining term and establishing the desired energy estimates. The goal is to establish a bound on the energy of the solution, which is essential for proving stability and convergence results later in the paper. The derivation of an estimate for the solution to a boundary value problem is crucial in understanding the behavior of certain mathematical models. The authors utilize various mathematical techniques, including integration by parts and the Sobolev embedding theorem, to obtain the desired estimates. The main objective is to find an expression for the solution nu in terms of y, where y is a function that satisfies specific differential equations. The authors first derive the equations for hi and hii, which are then used to find an expression for nu. They also use the solution formula 3.5 to obtain a relationship between gy and nu. The evaluation of nu in terms of y involves bounding the norms of various quantities, such as I2, 1, I2, 2, and I2, using the Sobolev embedding theorem and other mathematical techniques. These bounds are essential in establishing the main result of the lemma, which provides estimates for the norms of nu, and nu. The authors show that the norm of nu can be controlled by the norms of y, a tau y, and h, and similarly, the norm of nu is controlled by the norms of y, a tau y, and h. These estimates are critical for understanding the behavior of the system under consideration and will likely be used in subsequent sections of the paper to derive further results. The first estimate of the lemma is derived from lemmas 3.5, 3.7, and 6.1. The first equation in 6.3 is utilized to obtain an expression for the second estimate, which is combined with the first estimate, lemmas 5.1 and 6.1, and the inequality barred BLS12H, barred BLL1 is less than or equal to 1 minus 2O, minus 1 2, barred BLS12 plus O, barred BLL2 to yield the second estimate. The energy functional E, T, is defined as the sum of several terms, including the squared L2 norms of y, a tau y and x, as well as the inner product of a tau y and f. The parameter lambda is introduced to ensure that the energy functional satisfies the inequality stated in lemma 6.6, which is proven by evaluating the term nu s equals 1, 2. The solution formula 3.5 is applied to obtain an expression for nu, which is then used to derive an upper bound for nu s equals 1. This bound is expressed in terms of the L2 norms of x, y, and h, as well as the Sobolev embedding theorem. The proof of proposition 6.2 is continued by fixing the parameter lambda in the energy functional E t as lambda equals lambda 0 . The time derivative of E t is then expressed as the sum of three terms I1 I2 and a term involving the inner product of y and y . The terms I1 and I2 are bounded using lemmas 6.1 and 6.5, and the Gronwall's inequality is applied to obtain the desired estimate. Throughout the page, various lemmas and inequalities are utilized to derive the desired estimates, including the Sobolev embedding theorem and the inequality bard BLS12H, bard BLL1 is less than or equal to 1 minus 2 0, minus 1 2, bard BLS12 plus 0, bard BLL2 . The page concludes with the application of Gronwall's inequality to obtain the final estimate. The authors focus on proving theorems 2.3 and 2.4, ensuring the uniqueness of solutions to the initial boundary value problem. They assume x1, tau1, and x2, tau2, are solutions in the class 2.3, satisfying the stability condition 1.5. By defining y equals x1 by 2 and nu equals tau1 tau2, they aim to show that y equals 0 and nu equals 0. The authors derived two systems of equations, 7.1 for y and 7.2 for nu. They note that, although x satisfies 5.1, x, tau, is not a solution to the problem in general, requiring a modification of the energy estimate obtained in proposition 6.2. A modified energy estimate is presented, where the time derivative of a functional involving y and its derivatives is equal to I1 minus a boundary term. The boundary term is evaluated using a new lemma, lemma 7.1, which provides an estimate for the boundary term, involving the fundamental solution phi and an error term I2, bounded by norms involving y, tau, nu, and their derivatives. This modified energy estimate is crucial in establishing the uniqueness of solutions to the initial boundary value problem. The section commences by establishing an identity through the utilization of hyperbolic equations and boundary conditions, resulting in an expression for G. This identity is then employed to correlate with the findings of the previous section, notably lemma 6.4. The energy estimate from proposition 6.2 is demonstrated to be valid in this context, and an upper bound for E t is derived. By applying Gronwall's inequality, it is proven that E t is equivalent to 0, implying that the solution must be the trivial one, y equals 0. This completes the proof of theorem 2.3. The subsection concludes by emphasizing the uniqueness of solutions to the problem 1.1, 1.3, in the case G equals 0 without assuming the stability condition 1.5. The authors delve into the analysis of a specific problem related to the stability and uniqueness of solutions in a particular class of equations. They introduce lemma 7.2, which states that if the stability condition 1.5 is not satisfied, then the solution to the problem 1.1, 1.3 must be x, s, t is defined as x0, s, and tau, s, t is defined as 0. This result is further generalized in corollary 7.3, where it is shown that if the initial data satisfy x1, s, is defined as 0, then the same conclusion holds. The authors then proceed to prove theorem 2.4, which asserts that the solution to the problem 1.1, 1.3, in the class 2.3 is unique. This uniqueness is established by considering two possible scenarios. Either x1, s, is defined as 0, in which case corollary 7.3 applies, or x1, s, 0, in which case the stability condition 1.5 must be satisfied, and thus theorem 2.3 can be applied to establish uniqueness. Finally, the authors present lemma 8.1, which provides estimates for the tension tau. This lemma states that if a certain condition on x, t, is met, then the solution tau to the boundary value problem 1.4 satisfies specific estimates depending on the integer j. These estimates are crucial for further analysis and applications of the problem at hand. The evaluation of the term partial differential jt tau, a solution to the boundary value problem presented in equation 8.2, involves deriving pointwise estimates for partial differential jt tau, considering two cases. J is less than or equal to m3 and j equals m2. For j is less than or equal to m3, the authors use the Sobolev embedding theorem to establish that aj, t, is bounded by a constant. They then apply lemma 3.5 with alpha equals 0 to obtain an estimate for barred BL partial differential jt tau, t, barred BLL infinity, which is also bounded by a constant. In the case where j equals m2, the authors utilize the estimates obtained in the previous step and apply lemma 3.7 with alpha equals 0 and p equals 2 to derive an estimate for barred BL partial differential m2 t tau, t, barred BLL2. This estimate is also bounded by a constant. The authors proceed to estimate barred BL partial differential jt tau, barred blam 1j by using equation 4.1, and evaluating barred BL partial differential jt tau, barred black plus 1 inductively on k for 0 is less than or equal to k is less than or equal to m2j. They show that it is sufficient to evaluate barred BL partial differential jt tau, barred BLYK, which can be bounded by barred BL partial differential jt tau, x, 2, barred BLYK plus barred BLHJ, barred BLYK. For the case k equals 0, the authors use the estimates obtained in the previous steps and apply lemma 4.11 to bound barred BL partial differential jt tau, x, 2, barred BLY0. This term is shown to be less than or equal to barred BL partial differential jt tau, barred BLL2, barred BLX, barred BL2x4. The evaluation of a specific mathematical function is examined, focusing on its behavior under different conditions. When k equals 1, an upper bound is established for the norm of the function's derivative with respect to time, leveraging the norm of the function itself and its higher-order derivatives. For the case where 2 is less than or equal to k is less than or equal to m2j, a similar upper bound is derived, with additional constraints imposed on the function's derivatives. The authors then evaluate two integrals, I1 and I2, which represent distinct components of the overall function. For I1, two scenarios are considered: when j is less than or equal to m4, and when j equals m2 or m3. In both cases, I1 is shown to be bounded by a constant. Similarly, for I2, two scenarios are examined: when j is less than or equal to m3, and when j equals m2. Again, I2 is demonstrated to be bounded by a constant in both situations. By combining these estimates, the authors obtain an overall bound for the norm of the function's derivative with respect to time. This bound depends on the norms of the function and its higher-order derivatives, as well as the norm of the time derivative of the function. The result provides valuable insight into the properties of the function under various conditions, with implications for understanding its behavior in different contexts. In the case where j2 is less than or equal to j-1 equals m-3, the expression I2, j0, j1, j2, j, is similar to I2, j0, j1, j2, j-1. This leads to the conclusion that braceleft big, barred BL partial differential jt tau, barred BLL infinity, barred BL partial differential j1tx, barred BLX3, barred BL partial differential j2tx, barred BLX3, lesser similar, barred BL partial differential j0t tau, barred BLL infinity, barred BL partial differential j1tx, barred blam minus j1, barred BL partial differential j2tx, barred blam minus j2 holds true. When j equals m-2, it is shown that braceleft big, Bard BL partial differential m minus 2 t tau, Bardy BLX1, lesser similar 1 holds. The discussion culminates in the proof of lemma 8.2, which provides estimates for the tension tau in the case where m equals 4. The proof relies on the inductive hypothesis and previous lemmas, particularly lemmas 4.3 and 4.10, to establish the desired bounds. The estimation of Bard-BL tau, t, Bardy BLX30, lesser similar 1 and Bard BL diaresis tau, t, Bardy BLX10, lesser similar 1 begins by confirming the validity of the estimate Bard-BL tau, Bard BLL infinity, lesser similar 1 in the proof of lemma 8.1. This is demonstrated through the equation for tau, showing that tau lesser similar x diaresis x plus s x x plus x 2. The section then derives similar equations for tau and diaresis tau, highlighting the significance of these estimates. The proof is completed by noting the additional weight SWA used due to the lack of an estimate for Bard BL partial differential Tx, t, Bard BLL infinity. This lays the groundwork for the evaluation of initial values, which is discussed next. The authors leverage lemmas 4.2, 4.7, and corollary 4.13 to derive norm estimates for a tau x and a tau x in various spaces. Specifically, they establish inequalities bounding the L2 norm of a tau x by the L infinity norm of micro and the L2 norm of A2x, as well as the x1, x2, and xm norms of x and x. These estimates are crucial in obtaining the desired bounds for the solution to the problem posed in equations 1.1 and 1.2. Next, the authors prove lemma 9.2, which states that for a positive constant m and an integer m is greater than or equal to 4, there exists a positive constant c equals c, m, such that if x, tau, is a solution to the problem satisfying certain bounds, then the xm norm of x is bounded by c. The proof involves an inductive argument, where estimates are established for the norms of partial differential jtx for j equals 2, 3, m. For m is greater than or equal to 5. Lemma 8.1 is applied to obtain an estimate for the L infinity intersection xm1 norm of tau. The product rule is then used to evaluate partial differential jtx and partial differential j1t tau, along with the previously derived estimates. By recursively applying these estimates, the desired bounds for the norms of partial differential jtx and partial differential j1t tau are established. In this section, the authors establish the stability of solutions to a specific system of equations using a priori estimates. They prove that for any integer m greater than or equal to 4, there exists a positive constant c2 such that if a regular solution, x, tau, satisfies certain conditions, then x, t, m is less than or equal to c2. The proof is divided into two cases. M is greater than or equal to 5 and m equals 4. For the case m is greater than or equal to 5, the authors employ induction on j, where 3 is less than or equal to j is less than or equal to m plus 1, to demonstrate that for all j in this range, the sum of partial differential mltx, t, xl is bounded by a constant. This is achieved by evaluating partial differential mjtx, t, xj, which can be expressed as the sum of three terms: partial differential mjtx, t, L2, partial differential mjtx, t, xj2, and s(j) partial differential mjtx, t, L2. The authors then estimate each of these terms using various lemmas and the stability condition, 1.5. They utilize the assumption that the solution, x, tau, satisfies the stability condition in the given bounds on x, t, m1 and partial differential m1tx, t, partial differential t. Through this process, they demonstrate that x, t, m is less than or equal to c2, thereby proving the stability of solutions for m is greater than or equal to 5. The case m equals 4 is handled separately, as it requires different estimates for the derivatives of x, t. The authors use lemmas 8.2 and 9.1 to obtain bounds on the derivatives of x, t, and tau, t, which are then used to establish the desired estimate for x, t, 4. This completes the proof of lemma 10.1, which provides a priori estimates for solutions to the system of equations under consideration. The evaluation of the second term in equation 10.3 is crucial for understanding the behavior of the system described by hyperbolic equations. The authors introduce a new quantity, micro, s, t, as defined in equation 10.4, to convert estimates for time derivatives into spatial derivatives with less weight of s. This approach allows them to estimate the second term using various lemmas and corollaries established earlier. For the case j equals 3, they use lemmas 4.7 and 8.2, along with corollary 4.13, to obtain an estimate for barred BL partial differential m-3tx, t, barred BLx1, less or similar 1. In the case of 4 is less than or equal to j is less than or equal to m, they apply similar techniques, utilizing lemmas 4.7 and 8.2, and corollary 4.13, to derive the estimate, barred BL partial differential m-jtx, t, barred BL-2, less or similar 1. The paper then proceeds to evaluate the last term in equation 10.3, by applying the differential operator partial differential j-2s partial differential m-j plus 2t to the hyperbolic equations for x, leading to an estimate for barred BLSJ2 partial differential JS partial differential m-jtx, barred BLL2, less or similar, barred BL partial differential m-j-2 tx, barred BL-2 plus, barred BLSJ-2 partial differential j-1s, tau, partial differential m-jtx, barred BLL2 plus, barred BL, partial differential m-jt, a tau, x, barred BL-2. These estimates are essential for understanding the behavior of the system and for proving the main theorem of the paper. The authors provide a proof for lemma 10.1 in the case where m equals 4, divided into several steps. They begin by noting that, according to lemma 3.4, the quantity micro defined by equation 10.4 satisfies micro s, t, asymptotically equal 1. First, they estimate the norm of x, t, in x2 by rewriting equation 10.5 as 10.6 and differentiating it with respect to s. This leads to the conclusion that micro L2 is less than or equal to m diaresis x, L2, which is in turn less than or similar to 1. As a result, x, L2 is also less than or similar to 1. In the second step, the authors differentiate equation 10.6 twice with respect to s and take an inner product with x. This yields an estimate for s micro L2, which is less than or similar to s m diaresis x, L2, sx, L infinity, and x, L2. Since these quantities are all less than or similar to 1, it follows that s micro L2 is also less than or similar to 1. Utilizing these estimates, the authors demonstrate that x, t, x2 and micro, t, x2 are both less than or similar to 1, thus completing the proof of lemma 10.1 in the case m equals 4. This result is crucial for establishing the stability of the solution to the equation under consideration. The research paper estimates various derivatives and functions, starting with deriving an estimate for barred BL partial differential tx, t, barred BLx1. This involves differentiating equation 10.6 with respect to t and taking an inner product with x. The process then leads to an estimate for barred BL micro, barred BLL2. The analysis proceeds to estimate barred BLS12 micro, barred BLL2, involving another differentiation and inner product. This, in turn, is used to estimate barred BLx, t, barred BLx4. The paper also discusses the estimation of barred BL partial differential tx, t, barred BLx3, which involves the differentiation of the hyperbolic equations with respect to s and t. Throughout, the derivations rely on previously established estimates and the properties of the functions involved. The proof of theorem 2.1 focuses on establishing a priori estimates for the solution, x, tau, to the initial boundary value problem. To begin, estimates for the initial data and the solution are derived using lemmas 9.2, 8.1, and 8.2, which yield the bound x 0 m plus tau 0 m minus 2 asterisk operator less than or equal C0. Next, the estimates in 10.1 are proved for 0 is less than or equal to t is less than or equal to t, again relying on lemmas 10.1, 8.1, and 8.2 to demonstrate the desired bounds. A crucial step in the proof involves applying proposition 6.2 to derive the energy estimate, 10.12, which relates the energy at time t to the initial energy and the integrals of certain terms over the interval 0, t. This estimate is essential in establishing the theorem's claims, and its derivation requires meticulous attention to technical details and mathematical derivations. Through these careful calculations, the theorem's estimates are rigorously justified, providing a solid foundation for further analysis. The proof of lemma 10.2 demonstrates that E 0 plus S1 0 is bounded by C0, and S2 t is bounded by C2 for 0 is less than or equal to t is less than or equal to t. This proof involves a series of mathematical manipulations, leveraging lemmas 9.1 and 4.3 to evaluate S2 t. In the case m is greater than or equal to 5 and m equals 4, the evaluation of S2 t is detailed, utilizing Sobolev embedding theorems and the application of lemmas 4.3 and 4.6. The boundedness of f t and h t is also addressed, applying similar mathematical techniques to ensure that all terms are bounded by C2. This rigorous mathematical development underpins the lemma's key statement, showcasing the technical depth and precision required in the field. The estimates derived in previous sections culminate in the conclusion that S2 t is bounded by C2 for 0 is less than or equal to t is less than or equal to t. This implies that E t is bounded by C1 E C2t, C0 plus C2t. Additionally, the bounds x t m1 is less than or equal to C0 plus C2t and tau s t is greater than or equal to 2C0 C2t are established. The constants m1 and m2 are defined as 2C0 and 4C0 C1, respectively. By selecting a sufficiently small time t, such that C2t is less than or equal to min C0, C0, log 2, the solution, x tau, satisfies the estimates in theorem 2.1 for 0 is less than or equal to t is less than or equal to t. This completes the proof of theorem 2.1. The remainder of the page introduces declarations and auxiliary results, which facilitate the proof of subsequent theorems. This video presents a detailed summary of the research paper, focusing on its key concepts, methodologies, and findings. The study explores an extensive list of techniques used in various fields to provide a comprehensive overview for researchers and stakeholders. The paper begins by defining key terms and concepts that are crucial to understanding the subject matter. It then delves into the methodologies employed, explaining their purpose and significance in detail. These methods include statistical analysis, experimental design, and computational modeling, which are all integral components of the research. The findings section highlights novel ideas and significant discoveries made during the course of the study. These findings are supported by equations, algorithms, and mathematical concepts that are summarized efficiently to ensure clarity without losing essential details. The research also incorporates data from figures, tables, and graphs, condensing this information into a concise format that maintains the essence of the original content. The study acknowledges potential limitations and assumptions, as well as areas for future work. This demonstrates the author's commitment to transparency and their awareness of the need for ongoing research in the field. The language used throughout the paper is precise and domain-specific, reflecting the author's expertise in the subject area. The structure of the content follows a logical flow, starting with introductory concepts and progressing through methodologies, findings, and conclusions. In conclusion, this video provides a succinct yet detailed summary of the research paper, capturing its technical accuracy and depth while making it accessible to a wider audience.